Hey, John here. Let's take a look at the big picture. What stuff goes in what files in an FPGA project, from scratch, from the beginning? How does everything come together?
As always, a big thank you to all my Patreons for helping out with everything on this channel. If you'd like to become one, you can click on a link below this video in the description on YouTube. Remember where we're coming from here. This is about the Lattice ICE40HX family of chips, okay? I'm dealing with the ICE40HX4K specifically in the 144-pin quad flat package, and that means it has about 100 I/O pins spread around these 4 I/O banks. Now, this is a pretty good high-level picture of this specific chip. We can make a more general view of this that'll apply to most FPGAs, okay? And that's something that looks a bit more like this. So inside this cloud, you have all these lookup tables in the routing mesh. Let's just stick it all in one big cloud. That represents the vast majority of what all the code you will write using an HDL like Verilog or VHDL. This is really what you're dealing with when you're writing a lot of that code. Now the vendor will provide these hard modules that you can use, like pins, so you can get data in and out of the chip. And in order to move from LUT and the routing matrix and stuff like that that's in here out of the chip, you go through one of these programmable I/O blocks. Okay, so the ICE40HX4K that has 144 pins has about 100 then of these programmable I/O blocks. And as I've noted down here, when you configure a programmable I/O block, or a pin specifically, you're going to put an entry in what's called the pin configuration file. All right? Now, I've drawn them in a square box here, along with these other square boxes we'll talk about in a second, because you can also use what we call a special module inside your HDL language you've chosen. In my case, it's Verilog. So if you don't know what a module is yet, we'll see that soon enough. The short of it is, anytime you express a piece of a circuit, you're creating a module. Modules have inputs and output signals, and then it has, combinational and sequential logic within it to express the functions you want to achieve. Now, these things, I mark them as special because what happens is these are not things that you can see the source code for, because there is no source code. These are created directly in hardware. So what happens is the vendor tools, or whatever tool you're going to use, has to know what these are. And when you tell it you want to create an instance of a module, like I'm going to create what is normally called a top-level module in a minute, and it'll have some wires coming in and wires going out, and then it'll have its functionality, right? Well, there's a thing that looks like a module that I can create as part of my application, in Verilog in my case, and I can say I want a PLL module, and I want to set these signals going into it and some other signals coming out of it. So I'm going to create a PLL module. But my point is there won't be source code. I'm not going to be able to see it because there isn't any. The tool set itself provides these special modules. And in the case of the ICE40HX, those modules are defined down here. Right here where it says, here's a logic cell description. If I want to, I could manually create a LUT4 module, and I would have these signals called I/O, I1, I2, I3, an enable, a set, and a reset, and so on. These signals, these wires would be going into and out of that module if I wanted to work at that level. Nobody does. This is just ludicrous. Don't do this. But the tools That's why, by the way, you use this hardware description language. The whole point of using a compiler is to be able to write in a higher level language and then have it output. You can actually go in and see the output, and it says, I'm going to create a whole bunch of LUT4s, and each LUT4 will be interconnected like so in order to have the functionality that represents the kind of code that I'm going to write for a module, for example. Now, in order to connect them together, you go through this routing matrix. And again, the tool knows how to deal with this stuff. The routing and the LUTs, that's what the tool, the main thing the tool really, the compiler can really do for you. Okay? But once you start dealing with like, oh, I want to know that I have a special routing pin or a signal that has to be globally routed throughout the entire chip because a whole lot of different things are going to use it, and I want to make sure there's a low latency path so everybody gets the same like rising and falling edge at the same time. Well, if I'm going to do that, I'm going to create a GBuff module, and I'm going to configure it the way it describes down here somewhere. This is how the PLL looks, and these are the signals on that. If you create a where is the GBuff? It'll be in here somewhere. System I/O, programmable I/O, register block. Here's all the signals for the PIO block and so on. I guess I chose a bad example. Wow, it doesn't actually give it to you in here. Actually, the reason they don't is because it's probably in a different manual. What happens is you end up having to go look at other manuals to get more details on all the specific modules and stuff. So I picked a bad one, all right? Sorry. It turns out the ones that are explicitly defined and discussed in this particular document are the LUTs and the other ones we just scrolled by. So anyway, my point is, these things look like modules, but they're special because the compiler knows, oh, he needs to use a PLL, and that's a real component in the physical hardware. So I'll configure the the output of the compiler to use one of the actual PLLs. I can't create one. There has to be one in the FPGA. Okay, same thing with these global buses. The EBR stands for Embedded Block RAM. There's a couple of dozen of these things inside the HX4K chip, and we will use them if you want to. You can use it to create a FIFO, or if you're going to create a small CPU or something and put it inside here and express all the functionality of the CPU with LUTs and stuff. You can use these as a cache, or you can use them as your register file and stuff like that. Hopefully, we'll get to the point where we can do that in this series. I'm very excited about tinkering with that myself. Bigger FPGAs, not the one that we're dealing with here, the ICE40HX does not have DSP blocks and CPUs and stuff like that. Bigger FPGAs have them. A lot of FPGAs have DSPs, and those are multiplier accumulator units so that you can use them to do math without having to get actual like a floating point unit in there, which would be more complex, or a whole CPU, which you can get as well. Again, you pay more for those FPGAs, but you can get them. Xilinx has a Zinc series, ZYNQ is how they spell it, that has ARM processors and stuff like that in there. I think they have Spark processors, and we're starting to see RISC-V processors in some vendors' FPGAs nowadays as well. Other common modules you could find in there, these are generally called hard IP, IP referring to intellectual property of the manufacturer. That's a common term that a lot of people use for these things. Other common ones will include Ethernet interfaces, SPI, I2C, serial UARTs and things like that. Okay, and of course that's why, other than the number of LUTs and the number of I/O pins and whether the LUTs are 4 in or 6 in or 3 input or whatever, those are the things that differentiate different FPGAs and different vendors, right? There's the total speed, total number of LUTs, how many inputs a LUT has, and what kind of hard IP does the FPGA have. So that there's your differentiation, okay? So, big picture. We're going to focus on writing code that sits inside this cloud. And I would love to start here. I would love to focus on that and get into it, right? The problem with that is that you can't really do anything with an FPGA unless you're connecting up I/O pins, because any circuit that has no inputs and no outputs doesn't do anything. It's not fun. In fact, the compiler will figure out that it has no inputs and outputs if you create such a thing, and it will optimize that all the way down to not doing anything because it has no purpose. That's, it doesn't take a lot of optimization to do that, but that is what will happen. It's a little annoying, because it means that we have to kind of like on day one jump into some annoying and sophisticated stuff. I'm sorry, but we're going to have to just deal with this. So let's do this. I've created a couple of example programs. And what I'm going to do is just simply connect one pin, an input pin that comes in here, goes through the routing mesh, goes through a LUT, doesn't do anything at all, turn around, go back out. Okay, so I'm going to have a single bit input that is just routed right back out another pin, a single bit output. And I'm going to put an LED over here on the output. I'm going to put a push button on this input. And this is easier than Blinky. All right, it's the don't do anything but just move this signal through here and back out. What we will have achieved in doing so is we'll take a look at what goes inside the pin configuration file, because we're going to have to configure 2 pins in order for this to work. We're going to have to compile a program that has 1 line of code in it that says the output equals the value from the input. We'll have to run all the tools, and then we'll have to program the FPGA and get all that stuff to work. This is really the hello world program of an FPGA. Blinky is more sophisticated, and I've got that in the same repo as these examples. We'll talk more about Blinky in another video because it'll require a little more thought and discussion, because if we bring a signal in here and just send it back out, we're not really doing anything. We're simply connecting. If you want to blink something on and off, what we need is a circuit that periodically does something. And it goes on and off and on and off. And that means we're going to need to be aware of time, and we're going to have to figure out how to create a delay and all these other things. It's not hard once you know how, but it's not as easy as a simple combinational circuit, which is what we're going to do on day one here, which is simply here's 1 or more input bits that go through basically a truth table lookup. That's what a LUT really is. Decides what to do with its logic, calculate. Maybe I'm going to take 2 binary inputs and say A ANDed with B and output the result of that over here, or something like that. All right, that would be more sophisticated, but it's still a combinational circuit. It has no state. It has no concept of time. All right, so let's start with combinational circuits, not sequential, and just look at how the compiler works and get used to what's going on, how to configure it, how to build our projects. So here's the GitHub repo I set up specifically so we can focus on and share these files to get things started here, all right? I got these minimal 1, 2, and 3 examples and this half adder. That's what I'm going to talk about today, starting with minimal number 1, okay? Now you go ahead and clone this and grab the files. You can compile them. I've already talked about how to install the tools that you need to build all this stuff in previous videos. If you haven't seen them yet, go to the link to the playlist in the description below this video on YouTube to go back and follow along what's going on. As many of my projects have, a make file. There's a README to remind me what to say, remind me what this particular project does. So what is this going to do? It's a basic module that's going to connect an input, which is a button, to an output, which is going to be an LED. Note that by default, the FPGA pull-up resistor is not enabled on the button input, therefore it is not stable. Okay, now remember, in the documentation for the HX chips, if we look at the I/O block, there's a pad. That is the physical pad on the die that has a wire that goes to the pin that leaves the physical chip. That's where the wires really come out of there, right? So you have pull-up enabled with the pull-up resistor going up to VCC I/O, which is 3.3 volts. We already talked about the schematic of the 2057 project, which was built with all the VCC I/O voltages set to 3.3 volts. You can use different voltages, but I kept it simple. Everything's running at 3.3 volts for this particular tutorial, this particular project. Now, by default, this pull-up resistor is not going to be enabled. And if I have this configured as an input, and I've got a push button on here, and it's momentary, and I got the push button connected to ground, when I'm not pressing it, this pad is not connected to anything at all, and the voltage simply floats. This here is turned off, high impedance, because I've got an input-only pin configuration here. It's going to flow through this MUX and into the routing network and LUTs and wherever it's going to go in the design that I've created, okay? So if we don't have a pull-up resistor and this thing floats, it will chatter. Very high frequency noise will come in on here. And it'll actually look like the LED is getting bright and dim, because what it'll be doing is oscillating on and off because this pad is floating, and this gate here will be going hello, 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 depending on what you're doing here with what the schematic over here, what the circuit is doing with this pin, okay? Now, we can put a physical resistor external to the chip and pull it up or pull it down so it doesn't do that, or we can enable this pull up inside here, which is very handy because that means you have 100 fewer pull-up resistors if all the pins are inputs on your FPGA, which theoretically would be useless. You need some inputs and some outputs to do useful work. My point, though, is that that's 100 up to 100 fewer resistors on the circuit board because they've done this inside the FPGA, which I'm going to take advantage of. But you need to keep that in mind. You can't just ignore it because it might appear to work with an LED on there, but it will be inconsistent and flaky. Hence this note, okay? This is so minimal, we don't address that, okay? Now, let's open these files up in a regular editor here. What am I looking at? Here's my top level here. Minimal number 1. Oops. Let's go in here. Mess off the screen. Okay, here we are. How does this build work? Now remember, if you're using Make, just plain Make. I'm not messing with CMake and 100,000 other tools. Just Make. What will happen is it'll print out what it does as it goes along. If you don't want it to do anything, but you want to see what it would do, you can say Make -N. And in my head, I always think that that stands for not really. Okay? So what this is going to do now is that if you didn't tell me not to, I would have done this, then I would have done that, then I would have done this. These are the 3 steps we need to go through to create this top.bin file, this binary file. That's the thing that we're going to program into the FPGA to make it do what our program says to do. Now, as you can see, even if you don't know what's really going on here, you can see in here top.v, and there's an actual file. That's where our source code goes. That's what I'm going to create here. That's what's getting compiled. And you see this here, top.json, and then over here you see a top.json. Well, this thing here is the output of the compiler. And it becomes the input of the place and route. This thing's figuring out how to interconnect all the logic LUTs that Yosis, the compiler up here, decided have to exist in order to do what this thing says, all right? So, figure out what the LUTs need to be based on the source code. Figure out how to connect the LUTs together and output this ASC file. Then we say take that ASC file and convert it to a binary file that we're going to use to put on the FPGA, right? So you compile the thing, and then you place and route. Other tools call this PAR, P-A-R sometimes, but that's what's really happening. These are 2 very distinct pieces. Just figuring out how logically what has to happen, and then map that to a physical chip based on the constraints of its routing network and stuff like that, that a specific FPGA chip has in it. And place and route, of course, is the thing that's going to prune off, well, both of them, YOSIS and PNR, are both going to prune things off if they're not needed. And a lot of times you'll use a module that somebody else wrote, a general purpose module that might have, all kinds of features in there. But you may not use all the features. And what'll happen is it'll figure out that, hey, you're never using some feature X. Therefore, I have a whole lot of LUTs and logic and stuff that doesn't even need to exist, wasting energy and space inside your chip, and it gets optimized away. One great example is, and we'll write one maybe and have a look-see at it, if you just put an AND gate in the FPGA and nothing else, it'll need a LUT to do that function. If you take that output of that AND gate and you don't connect it to anything, it'll figure out that that function doesn't accomplish any useful side effects and remove it from your design. And you can actually count the number of LUTs and stuff like that. When this compiler runs, it prints out all sorts of stuff. And you can actually see what a number of resources are ultimately used, okay? Now let's look at what we're doing before we compile it. I guess that would make more sense, right? So what we're going to do is compile our top level module. We'll talk more about modules and the top level and all the roles of this in agonizing detail later on. For now, just understand that one single module has to represent, like if you're writing a C program, you have to have a main, right? Or a Java program. And I'm sure C# the same way, since it's the same thing as Java anyway. They all have this, like a main entry point. Start here, okay? Now, in Verilog, you don't normally have an official name of something. What you do is when you build it, you say, by the way, the top level thing is called whatever I decide to call it. I could have called it XYZ if I wanted to. It's overwhelmingly common to call the main top level module top. Okay? So I'm going to follow that convention. It's very useful, okay? You can always kind of keep your bearings at what you're doing. So, I've created a module called top. It has input and it has output ports. We'll, again, talk about what a wire is versus what other kind of things this could be and so on in another video. But for now, let's just focus on the fact that there is an input wire that I'm calling button 1. It's the wire that goes to the button. It's the input to my logic that this module is going to define. And I have another wire that's an output. It's going to leave the FPGA. And I'm calling that LED1. And the entire function, the operation of this application is to set the LED wire, the Boolean value, the binary value that leaves the FPGA out of the signal I'm calling LED1, set it to whatever the button says. So when I press the button and it becomes and the button shunts the pin to ground, it becomes 0, and the LED1 wire coming out of the chip will have a 0 on it. When I release the button, if there's a pull up or enough static and noise in the circuitry in the air to make it look like it's high, then the LED1 output will be 1. So this is what our module does. It has no really useful value here other than route a signal through it, like I said before. Now, if we compile it, we have these PCF files here that are going to be used by the place and route. Now I'm going to run this on my 2057 board. Now these make files that I have set up in here, as I mentioned before, I have multiple projects and they all share the same configuration stuff. Now it turns out that in order to support a different type of boards, like a 2057 board, the iStick board, or the UPduino, what I've tried to do is set up a system of stuff where the Verilog can be shared between all three of these different boards. So if you don't want to make a 2057 and you own a UPduino, I want to do a UPduino, okay, fine, that's great. But we have to do a little more planning to make sure that we can reuse our code on different FPGAs. The Verilog part of our code is incredibly portable. Remember this picture here. What goes in this cloud is very portable. All these little boxes over here are not portable at all. Okay? To some degree, chips in this from the same vendor might be able to use the same module specifications for their pins. Once they define a pin and a module, they might use it on different FPGAs. Certainly in the same family, like all the HX family of FPGAs have the same PIOs. Probably have the same G-bins and PLLs and EBRs too. They just have a different quantity of them. Okay? So your Verilog will be very, very portable. PLLs, G-bins, and block RAMs, stuff like that, and even these DSPs and CPUs would be if the chip had them on it, and if they were from the same vendor and the same chip family and so on, they would have very similar, if not identical, modules. These IP blocks, that a lot of times are called, they would be the same. Okay, but you change the package. Well, if you have a different number of physical pins, then clearly you're going to have a different number of PIOs. And what's worse, very unfortunately, is the way the tools work. When we look at the pin configuration files, you refer to the pins by the physical pin number coming out of the package. So if I have a 144 pin, FPGA, there'll be pins 1 through 144 in the PCF file. If you have the exact same chip with a different package, maybe you'd have a 64 pin package, then the pins will be 1 through 64. And a lot of times different functions are on different pins. So it turns out that the PCF files are rarely portable. Okay, so let's look and see what we have for the 2057. What I've got here is I say, look, I define each one of the pins I'm going to use. I got to set an I/O port called LED1 such that it maps to physical pin number 118, and then set the I/O port called button 1 to physical pin number 105. Now this is going to match my schematic for the 2057 board. We've looked at that earlier. If we look at the UPduino, we see, what do we got? LED1 is on pin number 39. It's going to be my output. And button 1 is going to be on physical pin number 23. Now, on the UPduino, pin 39 is hooked up to one. It has a single LED on the UPduino, and it has an RGB LED on there. So I've decided that the LED output will be connected to the green component of the RGB LED on the UPduino, and that's on pin 39 and so on. You need to know where these are by going to the sites. I'll put links below. In fact, go to the repo, the various repos at GitHub, where I have links to all the other boards and stuff that I refer to in here, right? So the iStick, the UPduino, and the 2057. For the sake of completeness, let's look at the iStick, because that has an HX1K on it, while I'm using an HX4K. So these all look very similar. We're just using different pins. And that's about as minimalist as we can get to support 3 different physical FPGAs with the same source code, which is this top.v file here, okay? So the only thing that is different about them in terms of the source code we write here is which pins are used for what, okay? Now, you also, if you want to change from one FPGA to another, what you need to do is you need to tell the compiler what chip, what die is in there, remember? And the PNR needs to know as well. So if you type, again, make -n, all along it says here's an ICE40. The Yoast knows I'm trying to do an ICE40. I'm targeting an ICE40 family of chips. And in this case, all these are ICE40 chips. All 3 of these systems have ICE40s in them. This one here, when I route it, I have to say it's got an 8K die in a TQ144 package. if we change the configuration, and I've talked about this in another video, over here in make local, you need to create a make local file. Mine looks like this right now. This is not in GitHub. You got to create this yourself. And you have to decide which one of the boards you want to put in here. You want a 2057, an iStick, or a UPduino. Each one of these has different sets of rules, and you can see in here there's an iStick rules, a UPduino rules, a 2057 rules, and inside here are the rules for the 2057. This is where the 8K and the 144, here's how you program it. Okay, and use this as the name of the pin map file. So you figure out, why does it know to get the data out of this file? It's all connected together with these make files. And if you can't follow it from there, you didn't follow it earlier on, what you do is you just look at this file here. This is the one we're using anyway. When we actually type make, it's the one in the current directory. Notice it says top is up one level. And notice I include, there's a minus that says don't complain if this doesn't work. That's what that's for. Go get the make local file and read it in. Go get the make rules file, read that in, and then follow these instructions down here. These recipes in order to do the compile and the programming of the board if you want. There's also a plot in here, and I think I showed that before as well. But now we're going to look at it in a little more detail, okay? So let's go ahead and compile it. And you'll notice it's a bit noisy, but it ends with the icepack command as we expected to create the binary that we're going to load up and run on the FPGA. Now, let's look at this thing here, top TB. The TB stands for test bench, which is a very common name for these test routines. Now, the test bench is going to have regular Verilog in it, but it's going to have a whole lot of stuff in here. This #1 and these dollar dump file, dump vars, things like that. This is not stuff that can ever exist inside of an FPGA. We say these things here, these guys that start with $1 and the pound signs, these are not synthesizable. The stuff that can exist inside of an FPGA is what I call the synthesizable subset of the language of Verilog or VHDL, right? The language can do a whole lot more than an FPGA can. And as I understand it, the language was invented not for programming FPGAs. Was invented to simulate an ASIC that somebody was designing. Later on, when FPGAs were invented, it became apparent that some aspects of this HDL, Verilog and VHDL, could be directly converted into a configuration file for the FPGA, which is kind of neat. But if you're just getting started, it can be very, very confusing. So the most important thing when you're just getting started, in my opinion, is to differentiate between that which is synthesizable and that which is not. Okay? Nothing in a test bench is ever designed, never intended to go into the FPGA. This is designed to be run in a Verilog simulator. And in a Verilog simulator, you can do things like wait a little while, then set X to 0. Then wait a little while, set X to 1. Wait a little while, and so on. And then I'm done now. Stop the simulation. Up here, it says when I'm simulating, save all the information about what is happening in the simulation into a file called toptb.vcd. And when you're doing that, what do you save? I say this means just dump everything that the simulation is doing. That is going to be a very large amount of data. especially in a complex design. But in a simple design, it doesn't really matter. Just save it all. It's much easier. Otherwise, you have to say, oh, I want to save this one, but not that one. It gets very complicated. Okay? We can be very wasteful in a very simple circuit and just say dump it all. So, what then does this really mean? Now, you noticed earlier I had a top module. It was in top.v. Okay? This is Verilog, and this is also Verilog. Okay, both of these have Verilog. These are legal Verilog programs. Okay? But this one here, by convention, if I wrote it and it's something.v, it's synthesizable. If it's something _tb.v, that's not synthesizable. This exists to be a test bench with common name. This is specifically created to test this guy up here. They both start with the same name, top. The top.v will have a module in it called top. Top.tb will have a module in it called tb that creates and tests a module called top. Okay, so that's the relationship between these guys. Let's see what that then looks like. There's the top module, and we just looked at this a minute ago. Let's get back on the screen. All right, here's your TB. Dock up here. This is, we'll talk more about simulation later. This is getting long. This has to do with how much detailed resolution do I want in my output when I save all these variables in this file. And I'm saying I want 1 nanosecond accuracy with a 1 picosecond scale. All right, this is a very common size. This is a very common scale to see in a lot of Verilog programs. Okay, so here's my TB module, which is, I lied. I didn't call it top TB. I just called it TB, which seems, when we look at the make file later on, we'll probably see why that is. But I lied. Get over it. It's called TB, and we'll see why later on. This makes it easier for us down the road. And inside here, we have a variable called X. We'll talk about registers and wires later. For now, it's a variable called X. This is how you instantiate. You bring in, you use, if it's a subroutine in a procedural language, you might say call a subroutine, right? Called top. And the way this thing works is I say, I need a top. I need a schematic. Go take the circuitry from top, from that module. I'm going to call this instance UUT, which stands for unit under test. That's just the name I use. Okay? When you create the top, here's what I want you to do with the wires, the ports, technically they're called ports, that the top module has declared. So if you go up here, see it has a button 1 and it has an LED. The input's a button 1, the output's an LED. I don't need to connect all of them if I don't want to. I say I don't care about those. Notice what I did here. I connected button 1 to my variable called X. And I remind myself that you don't actually need to connect them all if you don't want to. If you don't connect them, that means that the signals are simply undefined. And it'll show up in the simulation with a special indicator that says, I don't know what the value is here at this time. You cannot depend on it. Okay? Now, the outputs I don't care about with regard to testing in this simple test bench. I'm not going to look at the output and say, gee, I hope it's set to this value right now to verify that it's correct. All I'm going to do is exercise the inputs with the sole purpose of plotting it on my screen so I can look at it with my eyes. Later on, we'll write a test bench that has that connects outputs up into the top module and sends data in there. And then it will read the output from that module. And then when it's down here in this part of the code, we'll say, put this value in and make sure it says this other value out. And we can automate the testing with this thing, all right? It's more complicated. This is ugly enough as it is. We're just trying to light up one little LED here for now, okay? So let's keep it as simple as I can conceive it to be, right? So what do we need? We need a variable that I can set to values over the course of time with little delays in here and change it from 0 to 1 to 0 to 1 and so on. And I need to be able to send that variable into the module I want to test by saying, take this signal in this module, which is going to be an input into that module, and take the value of my x variable and send it in there, okay? Ignore what comes out, no problem. Now, down here, you can see I waste time, I set it to 0, waste time, set it to 1, and so on. I don't tell it what to do before I do this down here. So x is undefined until it gets here. Each one of these initial thingies, in terms of time, starts at the same time. This one I set off from this code down here because it's dealing with different kinds of housekeeping. All right, we'll talk more about this later. Bottom line is I have to declare what files to use, where the data is going to go, and what I'm going to save. While the simulation is running, I'm going to do this over the course of time. When I'm done, I'm going to stop it. Okay? To do all this, let's say make -n plot. What it's going to do, it's going to run Icarus. This is another compiler. Yosis compiles it so that we can run it in the FPGA for real. Icarus is a simulator, purely a simulator. It can do more than Yosis. Yosis can't compile this. This is not synthesizable. If you ran this into Yosis, I think it would actually stop. Well, I know you get an error, but I think the error would be, this is not synthesizable code. So it'll either say I'm ignoring it, or it'll just stop and say you're a dingus. Don't do this. Okay. So, but it is it can be simulated. Okay. So this simulator is going to simulate the code in these files, and it's going to save the result in here. Okay, what it's going to, it just compiles it for simulation is really what's happening. This then it'll run the simulation. And when the simulation is running, it's going to do this. It's going to create a file called this, and it's going to fill it in with a bunch of stuff. Notice this thing here is the same as there. This is going to run a thing called GTK Wave, which is a plotting tool. It just says draw a graphic image of all the waveforms in here. So if I say make plot, it'll do those three things. Right here, yeah, do this, that, and the other thing. It started up the viewer. It says here's the dump file, by the way, during simulation. A little debug output in there. It says the analyzer is started, and it opened it up in the middle of nowhere on my screen. So here it is. I think I've showed this once before with some of these hello programs, these simple test programs. You open up this hierarchy. Okay, remember the top thing was called TB? I open it up. What does TB have inside it? It has a unit under test. You click that. Down here it says, hey, this unit under test has these signals right here. It has a button 1 and an LED 1. So I can hold down the control key and select them all one at a time, or I can just go down here and hit Control A and select every one of them in this screen, type append to put them on the screen over here. Now, I said every delay with the pound sign, the pound ones that were in the source code, is 1 nanosecond. And then remember there was the slash and it said 1 PS. So let's put this in the background. Scroll back up here, right? 1 nano, 1 pico. So what that means is that this plot has data describing every picosecond in it. So if I scroll out, it's not until we get to 1,000 pico that we finally are at the end of that 1 nanosecond of delay that was in the program down here. Right there. There's wait 1 nano, set X to 0. Before I set it to 0, it was unknown. So in the plotter, it's unknown. That's red. I don't know what it is. Okay? It's something, but I just don't know. I can't know, as I never said it. What happens at 1 nano? I put a 0 in there. Why is LED 0? It's tracking button, because LED 1 equals button 1 in the top module. It just goes in, back out, okay? So this is how this all connects together. I wait a nanosecond, and then I change it to a 1, right here, wait another nano, set it to 1, wait a nano, set it to 0, wait a nano, and finish. So there's the, let me see if we can get it all on the screen at once here. Don't know, wait a nano, set it to 0. Don't know, set it to 0. Wait 1, set it to a 1. That's this right here. Then wait another 1, set it back to 0. Okay? Wait 1, and then terminate. So at 4 nanoseconds into the simulation, it terminates. Okay? That's what we're looking at on this graph. So when I debug my programs, I use this all the time. You're going to use this a lot more than you're going to be playing around with your FPGA, especially while you're learning early on. You just basically cannot debug these things if you're going to just write it and try and think your way through it. It is going to be a massive task. I mean, in theory, you could never test it. I mean, how many people can write something that works perfectly on the first try every time? And then write thousands of lines of stuff with no way to see anything. If you don't simulate it, there's absolutely no way to know what's going on. You can't poke a scope inside the FPGA. This is as close as you can get. You have to simulate what the FPGA would do and plot it and look at it on here to make sure it's okay. All right? So once you get over the initial excitement of, hey, I have an FPGA and lights can go on and off, when you need to program it for realsies, you're going to spend a lot of time creating these test benches and plotting your results. So that is where we're heading in the first round of application programs that we're really going to play with. All right? Because, I mean, this is everything. You got to simulate these things. We can also run this. I can log into my Pi on my bench, which I've called FPGA, so I can use dynamic DNS and log in to the machine called FPGA on my local LAN, and inside here I have an FPGA subdirectory, and I have cloned my repo from Github, and I can type git pull, make sure I'm all up to date, okay, and I can go into minimal 1 on here, and the reason I need to do this on my Pi is because my Pi is plugged into my 2057 board. I can't program a 2057 from my desktop, but I can from here. So I can type make and I can build the program. Same thing we just saw, blah, 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 blah. I got 2 warnings. I didn't notice that before. Oh, the warning is there's no clocks. This is a very unusual design. It's actually going to warn me twice about not having any clocks. There's the other one right there. The reason there's warnings in there is this is incredibly unusual to not have a clock, to not have a time, not have a counter. There's no sequential circuitry in here. That's so earth-shatteringly unusual that that's a real warning from the compiler. But because we know we've done such a foolishly simplistic thing, which is this, just connect it through in a combinational circuit. Yes, we have no clocks, okay? And then we're going to make prog, and it will go ahead and run the script that I cobbled together. It'll download the code into the FPGA, and now it says it's done. And we can go over to the FPGA, and we can play with the button and see if the light goes on or off. Now, at first we can see it doesn't go on and off, it's just on. Now, why do you suppose that is? It's because the pin is floating. We have to pull it up somehow. Now, the first thing we can do with this particular example program is we can pull it up physically with a resistor. Now you can see it works as expected. But, as you can see, I have to have an external resistor for this to work. And that's annoying. I don't want to have all these extra resistors on here. That's why we can use the internal pull-up. If we go over to minimal 2, and we look at the difference between this and minimal 1, we can see a difference. I've created an SBIO block, and inside here you can see hiding in there, I want to enable the pull-up in there. And what I've done, this is pretty nasty, complicated stuff, but if you look at what I've done here, I've got a wire called button 1 pull-up. And what it says here is it says I've got an SBIO block. It's going to be associated with the pin that's connected to the signal called button 1 up here. Okay? That's the input to this SBIO block. Now the output from the SBIO block, with the pull-up enabled, is going to be connected to button 1 underscore PU, which is this up here. Now I can connect LED 1 up to this configured fancy PIO block that has the pull-up enabled on it, instead of directly connecting it to button 1 like we did a minute ago. All right? Now this is pretty ugly, and it's very, very common to want to just turn on the pull-up. There's other things you can do with an I/O pin, and if you want to get fancy, you need to be able to put these things in your program. And then you need to figure out what these binary values are. You got to look them up in the manual, and you can figure it all up, and this gets really busy, okay? But it's so incredibly common that they give you a simple shortcut. This is minimal 3. In minimal 3, we go back to the original source code. This is what we had originally, without that I/O block in there. But what we can do is we can get fancy in the PCF file. Notice it says not just I/O LED 1 is on 118 and button 1 is on 105. This one says button 1 on 105 and yes, pull up, yes please. Okay, so I can turn on a pull up resistor if I want to in the PCF file. This makes it much easier. And the information about how to do this is in this web page over here, where they talk about the ICE40 chip and what the next P&R application, which is part of the YOSYS family of tools, right? What this thing is capable of understanding from the PCF file, okay? So if you look in there, we'll look at it some other time. It's actually pretty simple. We'll look at it in much more detail when we get fancier with the pins, okay? Bottom line is in there, it says, oh, by the way, I can support this kind of a mode. So if we type make in here, it'll compile it all over again. And now I can say make program again, and it'll use this new PCF. And now when we run this and we press the button, it works the way it should. And it does it with an internal pull-up instead of a physical external one, which is a big savings when it comes to, you know, soldering more parts on your board and stuff like that. At this point, we've seen what goes in a PCF file. We understand that this connects the physical pins of the FPGA to the ports in the top level module in our Verilog program. We've also seen that if we want to, we can tell the PIO block to enable a pull-up resistor by asking it to do so in the PCF file. We can also do it by directly configuring the PIO by instantiating a PIO module, an SBIO module is what it is called for the ICE40. And in there we can set certain bits and flags, rummaging through manuals, we can find out the values we're supposed to use in there to set the pull-up enable to on if we wanted to do it that way. Obviously, creating an SBIO is more complicated than doing it in the PCF file. So normally, I would put the pull-ups in the PCF file and move on. We'll see later on that there are other reasons we need to manipulate other configuration settings for the PIO, and we'll still need to be able to do that. We'll still have to be aware of how that process works if and when the time comes in our projects. We've seen the top level module. We've seen that we name the ports that come into and out of the top level module in our Verilog code, and we've connected that to the names of the pins in the PCF module. Next time, we'll spend more time focusing on what's going on inside this big cloud inside our modules, and less time worrying about how to connect them to the outside world. And we'll focus more on simulating our designs rather than running them on the physical chip, because as they get increasingly complicated, I mean, this is just trivial. Set an output equal to the input value. You can do that without debugging it. that's pretty safe. But as you get more creative, you're going to have to be able to simulate what the FPGA is doing so you can ask it what should be going on down in there so you can debug your code. And that will require us to focus a little bit more on the test bench code and how to organize our projects so that there's always a way to add a test bench to one of the modules so we can check them independent of other things in our design. Because you can't design the whole thing and expect it to work. We're going to have to test these individual modules incrementally as we go. And that'll be a skill we're going to have to build up in order to be able to be proficient at this whole thing. So, thanks for watching. I'll see you next time.